Welcome to the Royal Research Protocol for installing the Robotics Operating System, or ROS. Building complex robotic behavior requires a framework that can coordinate simultaneous data streams from sensors, motors, and processors. ROS provides that architecture, but it requires precision during installation to ensure these systems communicate reliably. By the end of this session, you will have a fully configured, locally hosted development environment. You will be ready to write, compile, and execute your own robotics applications right on your machine. This dashboard outlines the exact specifications required to run this software. You need to be running an Ubuntu long-term support operating system with an active internet connection. Your machine must have at least 2 GB of RAM and 20 GB of free disk space available. We will be working heavily in the Linux terminal. Command line syntax is literal, meaning a single misplaced space or missing hyphen will cause the system to fail. To avoid this, use the provided Royal Research repository links below to directly copy and paste all execution commands. Satisfying these exact hardware and operating system prerequisites ensures your machine is technically capable of hosting the ROS framework. Step 1 is connecting your machine to the official ROS servers. Software repositories act as remote digital vaults that hold all the necessary installation files. We have to specifically instruct your local package manager to target the ROS vault so it knows exactly where to pull the software from. Once the repository is targeted, we use the curl command to download a security key. This cryptographic signature proves to your operating system that the software payload we are about to download is authentic and safe to install. Now that the authentication signature is verified, run the sudo apt update command to refresh your local package index. If your terminal processes this request and returns a clean output without error messages, you have successfully completed a secure handshake with the ROS servers. Now we execute the installation command for the ROS Noetic desktop full version. This initiates the transfer of the entire core framework, pulling down the base operating system, adding complex simulation tools, and navigation libraries all at once. The ROS framework relies on hundreds of smaller underlying software libraries called dependencies. To manage these components, we use an internal tool called ROSstep. We initialize ROSstep using superuser privileges and then immediately update it. Warning tone: when you run the ROSstep update command, execute it exactly as written without the sudo prefix. Running the update step as root will corrupt your file permissions. Securing this automated pipeline ensures your system can resolve the necessary system-level libraries on its own, allowing the software to function without constant manual dependency management. The most frequent error new developers encounter is typing a valid ROS command and receiving a command not found output. This happens when the terminal does not know where the ROS executable files live on your hard drive. This flowchart shows a terminal node failing to recognize a ROS node until we introduce the .bash rc file. This hidden script dictates routing rules. Using echo, we append the setup script to this file, hard-coding the path directly into the system's settings. To apply these changes right now without performing a hard system reboot, use the source command on the .bash rc file. This forces the current terminal to adopt the new configuration immediately. Automating this environment variable up front insulates team from syntax and pathing failures during daily operations. With the system-wide software installed, we now create a Catkin workspace. This isolated directory is where your custom robotics code can be written, compiled, and managed safely. The Catkin compiler requires a specific directory hierarchy to function correctly. Using the mkdir command, we create the top-level workspace folder and place a central src, or source folder, directly inside it. Navigate into the root of this new workspace and run the initial build sequence by typing catkin make. Even though the source folder is empty, this command forces the compiler to automatically generate the remaining operational folders required for development. Next, we overlay this new workspace's specific setup file back into the automation engine we constructed earlier. Use the echo command again to add the workspace path into your .bash rc file. Establishing this isolated workspace allows you to test robotic behavior without affecting the core ROS installation. Now we initiate the final validation sequence. Type ROS core into your terminal and hit enter. This command launches the master node that coordinates all communication in a ROS system. This mockup displays the expected terminal output. The success indicator is the phrase "started core service" within the log, confirming the communication hub is online. Because the ROS core service must run continuously, this terminal window is now occupied. You must now open a new terminal tab to establish a secondary control channel for executing further commands. In this new tab, navigate to your workspace's source folder. We will test the compiler by creating a foundational package called Beginner Tutorials. We load this command with standard messaging dependencies like std messages, ROS-Pi, and ROS-CPP. Successfully compiling this new package while the core service remains active confirms that the dual-layered architecture is stable. To perform a final check, execute a localized search query by typing ROS-Pack list. If it returns the file path for your Beginner Tutorials package, the system has successfully recognized your new code. Keep the ROS step install command on hand as a troubleshooting tool. If you ever attempt to build a package and receive a missing dependency error, running this command against your source folder will automatically identify and install the required libraries. Guided by Royal Research, you have successfully completed the setup. Your hardware is now a validated ROS development workstation, ready for package development and behavioral coding.